Have you ever wondered where all the energy in the universe comes from? Ever thought about the power that fuels the sun and the stars? In our quest to understand our universe, we've uncovered a process so potent, so powerful, that it can light up the cosmos. This process is known as nuclear fusion. In the heart of every star, including our own sun, nuclear fusion takes place. It's a process where atomic nuclei come together, fuse into heavier elements, and release enormous amounts of energy. A dance of particles, if you will, that results in a brilliant display of light and heat. This is the same energy that has puzzled scientists and researchers for decades. The same energy that we, on our tiny blue planet, are trying to harness for our own use. And that's just the tip of the iceberg. There's so much more to this fascinating process than meets the eye. That power, my friends, is nuclear fusion, the process that lights up the cosmos. So what exactly is nuclear fusion? In essence, it's all about the heart of the atom. Let's break it down. The term nuclear refers to the nucleus, the tiny, dense center of an atom. Fusion, on the other hand, means to combine or merge. Put these terms together and you get nuclear fusion, a process where two light atomic nuclei come together to form a heavier nucleus. Imagine a dance where two partners, the light atomic nuclei, whirl around each other in a high-energy dance floor, the hot plasma. As the dance gets more intense, the partners get closer, overcoming the natural repulsion between them. At some point they collide, and in that moment of collision, they merge into a single, heavier partner. This is a simplified version of what happens during nuclear fusion. But what makes this dance so special? Well, it's the fact that when these atomic nuclei merge, they release a significant amount of energy. This energy comes from a small portion of the mass of the light nuclei that gets converted into energy, following the famous equation E=mc², where E is energy, m is mass, and c is the speed of light. This equation, proposed by Albert Einstein, tells us that mass can be converted into energy, and vice versa. This energy release is what makes nuclear fusion so powerful. It's like a super-efficient, high-energy dance that lights up the universe. From the blazing sun to the distant stars, they all derive their energy from this nuclear fusion dance. But this dance isn't easy to perform. The conditions must be just right. High temperatures and pressures are needed for these light atomic nuclei to overcome their natural repulsion and come together. That's why nuclear fusion mainly occurs in places like the sun, where the conditions are extreme. So, nuclear fusion is essentially the process of creating a heavier atom and releasing energy which powers the stars in the sky. Sounds simple, right? But the science behind it is anything but. Today, let's dive deeper into the intricacies of nuclear fusion, the process that powers our sun and could potentially power our future. Nuclear fusion is all about overcoming the immense repulsive force between atomic nuclei. The secret to achieving this lies in two conditions: extraordinarily high temperature and pressure. At these extreme conditions, the atomic nuclei have enough energy to overcome their natural repulsion and collide. When they do, fusion occurs, and a heavier nucleus is formed, releasing a massive amount of energy in the process. Now let's talk about temperature. We're not talking about a balmy summer's day or even the heat of a blast furnace. We're talking about temperatures in the range of millions of degrees. In fact, the temperatures required for nuclear fusion are so high that matter ceases to be in a solid, liquid, or gaseous state. Instead, it enters a fourth state known as plasma. In a plasma, the intense heat has stripped electrons away from their atomic nuclei, creating a soup of charged particles. It's within this energetic maelstrom that the conditions for nuclear fusion are ripe. But it's not enough to just have a plasma. To achieve nuclear fusion, the plasma needs to be confined long enough for the atomic nuclei to collide. This is known as the confinement time. Here's where the pressure comes in. High pressure, created either by gravitational forces in stars or by magnetic fields in man-made reactors, confines the plasma, keeping it dense and hot enough for nuclear fusion to occur. It's a delicate balance, one that scientists are still perfecting in the quest for a practical fusion power source. Despite its complexity, the science of nuclear fusion offers a powerful and efficient source of energy. Harnessing this process on Earth could revolutionize our energy landscape, providing us with a virtually limitless, clean source of power. Now, isn't that a future worth striving for? So, with all this energy being produced, you might be asking, how can we harness this power? Well, let's dive into the enormous potential of nuclear fusion. As we speak, researchers around the globe are working tirelessly to harness this stellar power source. Nuclear fusion, if achieved, could provide a nearly limitless and clean energy supply. Imagine a world where electricity is abundant, where power outages are a thing of the past, and where the energy that lights up our homes doesn't contribute to climate change. That's the promise of nuclear fusion. Current experiments, like those at the International Thermonuclear Experimental Reactor, are making strides in this direction. They're creating mini-suns on Earth, learning how to control them and extract their energy. It's no easy task, but the potential rewards are astronomical. The potential of nuclear fusion is immense, and if harnessed, it could light up our world just like it does the stars. Before we say goodbye, let's recap what we've learned about nuclear fusion. We started with the mystery, the enigma that is nuclear fusion, a process at the heart of our sun and every star in the cosmos. We then delved into the basics, understanding that nuclear fusion is a process where two atomic nuclei combine to form a larger nucleus, releasing a tremendous amount of energy in the process. Next, we uncovered the science behind the power, the intricate dance of particles that results in a release of energy far greater than anything we can generate through traditional means. Finally, we explored the potential of nuclear fusion, imagining a future where clean, limitless energy is not just a dream, but a reality. And there you have it, the power of the stars at our fingertips. Until next time, keep looking up and wondering about the universe.